We're going to start by making a new empty geometry object here. Just delete the file out, and we're going to do this entire thing in code. So let's start by putting down an attribute wrangle. I'm going to change this over to detail, so it's only going to run once, and we're going to write the entire thing here in Vex. So the first thing that I want to do is set up our parameters here based on our breakdown of the PDF. So we'll go into Edit Parameter Interface, and we can actually hide this Bindings tab here. I'm just going to make that invisible. We'll keep code where it is, and we'll just put everything here under code. So we'll organize everything into folders, and I'm only going to use 3 transformations here. More extensive implementations will use 6 or more. 3 is going to be just enough for us because trying to implement more in this time period is just going to be too much of a pain in the butt. So why don't we call this folder here named Variation 1, or Variation 0 rather. And then we will duplicate it. I'm just pressing the D key here. And we'll just change that to 1 and change that to 2. Now we'll build our affine transformations here. So I'm going to go ahead and grab a float vector 3, put it right here, and we'll call this T0 and label this transform. Just going to press D to duplicate that, and we'll change this to R0. We'll call that rotate. And we'll duplicate that once more, pressing D, and we'll call that S0, and type in scale. And we'll go into channels and change the defaults here to 1, 1, and 1. And then we are also going to want a float value here, which is our C value. So this will be called C0. Our label is going to be lowercase c. Default value, I'm going to say 0.5. 0. 0 is fine. This is going to have to be unique for every single variation, but I'm just going to default it to 0 here. We'll change it later. So we'll do that, and then I just also want to add one more folder below everything here, and that is going to be called Final Transform. So I am going to select this one here and say this is the end of a tab group here. And let's just take a quick look and see. Hitting apply. Perfect. So that's what I want. I want these 3 up here and then the final transform right down there. So now I can just select these and press the D key. And just put that there. We'll just go into the parameters and we'll change nothing because that's actually fine. Just ones right there is fine. And we'll press D one more time and we'll move these over into variation number 2. And then one more time, go into final transform. And here I'm going to replace the numbers with F for final. So RF and SF and then CF. Click apply. Just taking a look, making sure everything looks all right. Now what we'll want to do here is grab an integer to control our max iterations. So we'll just call this iterations. And we'll give it the label iterations. And why don't we default that to 10,000? And we'll click accept. We may need more later, but this is a good start for us, so we'll go ahead and save and continue. We'll start off by just bringing in all of our parameters here, and we'll just bring them in as one big code block. We will begin by saying integer iterations is going to be equal to channel quote iterations. and I'm going to declare that that is an integer. So just wrap that in parentheses, semicolon, and then enter. Now we need our transforms. So that's T0, R0, S0, and then C0. So I'm just going to go ahead and start writing. Vector T0 is equal to CHV, that stands for channel vector. And that's going to be equal to T0. Now I'm just going to copy this and we'll paste it right below. And just change this to R and S. And then change this to R and S as well. And now we need our C value. So float C0 is going to be equal to CH channel C0. Why don't we go ahead and leave a space between all these little groupings so it's a little easier to read. And just paste, paste. And we'll go ahead and change all of these zeros to ones and twos respectively. 1, 1, 1, and 1. 1, 1, 1, 1. And 2, 2, 2, 2, 2, 2, 2, 2. And then we'll paste one more time. And now I'm going to change all the zeros to Fs. So F, 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 and F. Okay, there we go. So we'll just go ahead and save, and then we'll work a little bit more. At this point, we do have our position, scale, and rotation information, and what we need to do is be able to convert that into a transformation matrix, which we can then apply to our point positions. To keep it simple, a transformation matrix is a grid of numbers that encompasses position, scale, and rotation all in one unit. We can then multiply the point position by that transformation matrix to move it around. You don't need to know much more other than to know that we are going to use this function here. And we can see that we have a function here that takes in position, rotation, and scale. And it just wants to know the order of translations and rotations are. So we're just going to say 0 and 0 because they're integers here. And you can see exactly what we need just to make transform, and then 0, 0, and then RT, R, and S. So we're going to make a transformation matrix for each one of our variations. I'm just going to go ahead and move this off to the side in case we need it. And we will just define this like this. Matrix is equal to make transform, parenthesis, and then we'll say 0, comma 0, comma T0, R0, S0, parenthesis, and semicolon. And I want to give this a name, of course, so that's going to be called M0. And now I'm just going to copy, and then we'll paste and replace. So just changing the 0 to 1, and then make sure we update all of these as well. And we'll just do that for the other variation. And then our final transform as well. All right, that's good. I think the next thing we're going to do is starting to define some functions. After that, we'll start creating some points and start moving some stuff around. So we'll save, we'll take a look at that PDF, and we'll come back in just a second. The first variation that we'll put in here is variation 0, and this is pretty simple. It's basically just a linear remapping. If x comes in, then x comes out, and if y comes in, then y comes out. So not really modifying anything. It just lets the affine transformation work and applies no variational stuff to it. So we will define this way. We're going to want to get a vector out, and the name of it is going to be called f0. That's the name of the function. And then it's going to take in a vector which is going to be our position. Now we need a bracket, and then make some space, and the closing bracket. And now we're going to say what we're going to return. So we are going to return, we're going to call this result. And now we have an actually defined result. So let's go ahead and do that up here. And this is going to serve as a template for the rest of our functions. So we will define a vector called result. And just leave it as is, or actually what we'll do is we'll set this to 0, 0, 0. So we've already initialized it. And now we want to do that simple remapping. So result.x is going to be equal to position.x. Result.y is going to be equal to position.y. And result.z is going to be equal to position.z. And that is our function for that. Now we'll take a look at our next function, and I'm just going to copy this as our template and just paste below. And we'll change F0 to 1. Scroll down a little bit, and let's bring up that paper, which I think is right here. There we go. And this is going to be the sinusoidal variation. So this is saying x is going to equal to the sine of x, and y is going to equal to the sine of y. Why don't we go ahead and label these as well. So commenting here, linear, and this is sinusoidal. And let me just check. I believe it was sine and sine. Yes, sine and sine. So result x is going to equal to the sine of position x, and result y is going to be equal to the sine of position y. Just doing one more check here. Yeah, sine and sine. Now we'll move on to the spherical variation. So we have 1 divided by r squared times x for x, and then 1 over r squared times y for y. And r squared, if we go up here, is going to be equal to the square root of x squared plus y squared. So let's go ahead and first we'll define r, and then we'll fill everything else in. And this one is called spherical. So let's call it spherical, label it, and then we'll paste our template in. And we'll just copy that and paste. And make sure we change this to F2. All right, let's go ahead and define R. R, so that is a float. R equal to the square root of position x times position x plus position y times position y. And take another look here. So we have 1 over r squared. So let's just go ahead and delete that. 1 divided by parenthesis r times r. And just check one more time what that was. And it is times position x. So multiply by position dot x. Now result y is equal to the same thing, but we're going to change position x to position y. And I'm just going to double check. Let's check it. Yep, that's right. So we're going to only do these 3 functions. If you've gone through this PDF, you'll see that there are 49 variations. There's a lot. Some of them are quite simple with easy variables and stuff, and some have a whole bunch of other stuff going on in here, things that we have to break out of the transformation matrix, these b values and e values and stuff like that. So it gets pretty complicated. There's some really beautiful stuff in here, especially the Julia ones that are really beautiful. Give you some really nice ones. Spiral's pretty cool too. Anyway, a lot of really cool stuff in here. So you're going to have to go on your own and add some of these things in and play around and see what you can figure out. But we'll get you started. All right, so just starting off on these guys here, we will save the file, and then we'll keep adding some more stuff. If you remember from the PDF and the explanation, the first thing that we need to do is define a point in space between -1 and +1, and z is going to be equal to 0. So let's go ahead and start a vector called position, and that's going to be equal to random, just typing any old random number here, and we're just going to leave it at that. I don't really care if it's between 0 and 1 or -1 and +1, so just leave it as is here. And make sure that position z is equal to 0. Now we need that c value, and that's going to be equal to some other random value. So something like that. And I think there was one other thing we want to bring in here, which is our max iterations. So let's go ahead and bring that in. If I didn't do it already, let me check the top. Oh, we did it. Okay. All right, so now we're going to create a loop. Okay, now we'll go ahead and start the loop. So here we go. We'll use a for loop for this, so we'll say for. Now we need to define an integer as our counter, so I is equal to 0, semicolon. Now the condition, while I is less than iterations, the loop is going to continue to run. And then finally, what's going to happen at the end of the loop, we will add 1 to I. And now in here is where we're going to do stuff. Okay, so we will define a random number. Whoops, where do we go? All the way back up to the top for something? There we go. Okay, so random. It's going to be equal to this random function of I. Okay, now we'll define some things to do with this. So we're going to randomly choose between these 3 variations. We're going to give them equal weighting. This is a kind of very hacky way to do this. There are better ways to do it programmatically than what I'm showing you here, but for the interest of time and simplicity, we're just going to do it in this very basic way. So we'll set this up first. So we'll just use if statements. If R&D is greater than 0.666, then we will do something. Now, if R&D is greater than 0.333 and R&D is less than or equal to 0.666, then we will do something else. And then finally, if R&D is less than or equal to 0.3333, we will do the very last thing. Okay, so the first thing that we would be doing is applying our affine transformation. So take our position, and that is going to be times equal to our matrix, so M0. Then we will be applying a function to that. So now we will be saying that position is going to be equal to the F0 of our position. Now all we need to do is copy and paste these and just change the zeros to 1. And one more time. And then finally, we are going to do our final transformation right here. So I'm just going to call this final xforms. And here, position times equal to mf. And then position is equal to, oh, that's it, just to ff. And we'll deal with color separately. Now, finally, we need to plot that point. So that's what we'll do here. We will plot the point. And we're looking for if I is greater than or equal to 20, then we will plot that point. We're going to add a point to our current geometry at our current position. And this is where we are currently at here. So let's go ahead and save this, and then we'll play around a little bit. Let's just do a quick test, make sure everything's working okay. I'm just going to press D and go into pixel mode here. Will give us more points to work with. Now we can play around with some of these variations and transforms. So I'm going to just go ahead and scale a little bit inward. I know that this is the linear variation in here. And why don't we go ahead and play around with some rotational values on the z-axis. Remember, most of this stuff works on a flat plane here. So we want to make sure if we're rotating, we're pretty much only rotating along z. We can try playing around with some transformations. This is pretty sensitive depending on which variation it is that is being adjusted. They'll all have different things going on there. We can just try a bunch of different values and see what happens. I'm just getting some weird looking stuff. Going back in here, let's maybe move down just a little bit. There we go, starting to get some kind of crazy looking stuff happening here. And a lot of what happens in terms of the look of this is really going to be dependent on which formulas you're plugging in for your variations. So don't expect that you're going to just end up with something great right away. It's all a lot of kind of black magic. Just playing around until you get some stuff that looks cool. Okay, so we'll just use this as kind of a starting point here, and we'll start to add the color stuff into here, and maybe we can play around just a little bit more until we find some setting that seems okay. I mean, we're kind of using some very basic variations here, so we really want to play around a bit more with what's available to us. All right, let's just leave it at this, and we'll start putting some color in here, and then we can continue to do a little bit more, but that's probably it, because part of your homework is going to be to take this, if you choose to, and extend it further, or you can start doing all kinds of other stuff. But it's quite a bit of work to keep going on this, so we'll just do a little more, and then we'll wrap this one up. Okay, so now we'll add this C value in here, and basically we are going to update C every time that we need to here. So in here, we already had a value that was C, and that's going to be equal to C plus C0 divided by 2. And make sure to put a semicolon there. I'm going to copy, paste that. And now this is going to be 1, and this is going to be 2. And then our final transform in here as well. C is equal to this plus CF divided by 2. All right. And before we go further with this, what we'll end up doing is putting a color ramp on here. So that's the other thing that we should be doing, is taking a ramp for color, and we'll just put this right under iterations, and we'll just call this CLR ramp. We'll click accept. We'll just go ahead and put some kind of wacky values in here. And you really want a lot of points in here. I'm only going to do a few. All right, so just a lot of colors. And we'll save the file and we'll do a little bit more. So we'll want to make sure that we add a color attribute in here first before we decide to set that attribute. So I'm going to, I think, maybe start right before we do the loop here. I'll just do it in here. We will add attribute, and we need the handle. The class is going to be a point. The name is going to be CD. And the starting value for that, the default value is going to be 000. And just click off of that. And let's see, what did we do wrong? We didn't do the closing parenthesis. And now when I middle click here, we do have CD. So now we will just set CD right when we do our final point. So before we add the point, let's make sure that we know the name of this point. So integer new point is going to be equal to that add point. And now we will set this attribute. Now I have to look this one up because I never remember what that is. We want set point attribute. Let's just put that off to the side. So set point attribute. Our handle is 0. The name is CD. The point number is new point. The value is going to be equal to the channel ramp expression. We're actually going to get that ramp. And channel ramp wants to know the name of the ramp, and that was called color ramp. And then it wants to know the position, and that position is going to be equal to C. And then finally, the mode is going to be set. And just click off of that. And let's see, what do we do wrong here? Find out 1, 2, 1, 2. Let's find out what we did wrong. Ambiguous function call. It doesn't like that. So let's see here. Oh, because it wants us to define this ahead of time. Okay, so why don't we just call this CLR? And we will just say a vector CLR is equal to that. Now that works. It just didn't know what to do with this whole thing. Didn't know what it was returning. So now that it does know, we have that, and now we need to go ahead and go back to our variations and start giving a new C value for every specific variation that's in here. And now you see that we're getting these weird, cool, wacky colors, and then we have this value here that we can use to offset and cycle through our gradient. So this stuff looks super cool, especially when you get millions and millions of points. I will just add another 0 in here. And it's going to take a while, excuse me. And I just can't get into it in the context of this lesson here, but I'm just going to tell you that there are a bunch of optimizations that we can be doing. It's just we just don't have the time to do all of that in here, and we don't have the time to really fully execute all this code. But these are the basic building blocks of this algorithm, and if you really want to take it far, you could spend quite a lot of time building this up and making tons and tons of cool stuff in Houdini. So let's just wait and see this last thing update here. Yeah, a little tough to see, but that's kind of where we're at right now. I thought we'd end here with just a really quick introduction for how you might render this. Going to go back to the Geo tab and we'll put a camera in the scene. We'll look through the camera and kind of zoom back out, maybe to around 7 or so. Then we'll go to the material palette and we will use a constant shader here. You should go ahead and do some researching on your own if you're interested into how to make a constant shader into an additive shader, which means that the pixel colors are actually going to add up together, which is going to give a totally different look to this. This is just an introduction, so we don't really have time to do that. We're just going to do some of the basic stuff. But the reason I use a constant shader is it doesn't take any lighting information, and it automatically is going to read in our point colors and alphas for us. So we'll just use that to start. I'm going to go into Object tab, go to my Geo, to Render and Material, and we'll apply that constant shader. Then we'll go to the Geometry tab, and this is going to control how big these points actually are at render time. So I want to render these as circles, not as spheres. So spheres aren't necessary because we don't actually have any lighting information. In point scale, I think 0.03 is going to do it for us. Now we'll go to our Output tab here, put down a mantra, and under Rendering Pixel Samples, why don't we go up to 6x6, and that's just to make sure everything's as crisp as we can make it. And then I'm going to go to Stochastic Transparency, and I'm going to disable that. We're going to end up using a lot of transparency in here. If we have Stochastic Transparency, it's going to try to optimize the rendering time there, but it's going to actually introduce grain because of that. So we would end up having to dial this up pretty high. And basically, I just render these things kind of without stochastic transparency. Just find that it's a little cleaner that way. All right, now we'll go to our render view here, and I'm going to disable updating on that, or progressive rendering, and then we'll just let it go. All right, take a snapshot, and then going into my material tab. Then I usually will dial opacity down quite a bit. And this is something that I'm always adjusting based on how many particles there actually are, or how many points we're actually rendering in the scene. And you'll see that when we get a lot of transparency in here, we start to be able to see through things and see a lot more detail. So maybe we'll live it somewhere like this. All right, I'm going to take a snapshot of that, and then I think all I have time to do is maybe we'll just look at, what is that, 5 million points? Let's see if we can look at 10 million and just see what that looks like. And we'll end up pausing the video here and just picking back up once the render is finished. So here we are at 10 million points. I've decreased the opacity just to compensate for the more points that we have. And just kind of scrubbing back and forth. I'm not sure if this is going to show up under compression, but you can see the results are much more clear. And just to give you kind of an idea of where you would be at for a pretty clean render, the stuff that I've been doing on my own is about 80 million points. So you have quite a ways to go before you're really hitting some stuff that is I'd say acceptably clean on here. There's other algorithms or other parts of the algorithms that kind of discuss how to get rid of noise, but they're not things that we're going to implement. Potentially that's stuff that you might want to do on your own, but this is as far as we're going to take this.